Okay, this evening on the bench, I'm having a look at this Brüel Kjær 2607. Basically, all it is an audio amplifier with a measuring device on it, a measuring meter. This was given to me by someone who collected a computer from me at the weekend. Someone who was interested in an HP computer that we had at work, that had been kicking around at work for years. And we didn't know what to do with it. No one could bring themselves to sell it or throw it away. So I advertised it, or made it an offer to Curious Mark. I don't know if you've seen his YouTube channel, and asked him if he was interested in it. He said no, but he knew someone in the UK who would be interested in it, which was this other chap. And he picked it up Friday afternoon, and he said, you know, do you want anything for it? I said no, it's a donation from work. I said, but if you've got any sort of like projects that you're not going to complete, or you just think that there might be something interesting for me to tinker around with that doesn't work, bring it along with you, and I'll be interested, you know, something to tinker with. So he did. He bought two pieces of equipment along. This is one of them. It's a lovely meter. It's I should think circa 19, probably maybe early 70s. Don't know the exact date on these things. And initially when I got it, it had it'd been stored in a damp area. It was pretty filthy. The meter glass had become loose, and there was a lot of sort of like mildew inside the display. But I've had the front panel off, and I've done this all off camera because it wasn't a particularly interesting video. I've had the front panel off, had the meter out, and actually you can actually access the front meter like that, and actually remove the dial and replace the screen, so you can actually do quite a lot of sort of upgrade of these units without actually taking them apart. So you can change the meters for, I suppose you could have a pass-fail meter if you wanted to, you know, if you were testing sort of like an audio amplifier and you're making sure the frequency response was in range. You could set a pass-fail display, you just drop it in for like QA or something like that. So it's obviously quite a sort of useful machine, but certainly back in the 60s, and obviously now it's pretty obsolete. Let me quickly run through roughly what it does. This is a preamplifier input, and that's designed to take their microphone inputs with the preamplifier, so you can take the frequency response of the microphones. We've got a direct input here, and they use these weird connectors. I don't know if you've seen them before. They remind me a bit of the early car aerial connectors. You've got a 3.5 banana jack in the middle, basically, and the outside is the screen. So you've got you can actually use a conventional banana jack in this port, and it will work fine. And then you just connect the ground position to here. So obviously it wouldn't be a very well screened lead, but I don't know what the name of these connectors are. I'm trying to find one. I found a couple of, but I typed in Brüel Kjær on the internet, but the connectors are like £40, and as I was given this meter, I'm not going to spend £40 on a connector. So at the moment I've been using just a banana plug here and another banana plug in the ground connection, so that works fine. So that's our normal direct input, unbalanced input. I think that probably is a balanced input input rather than an unbalanced. Then we've got gain control, which is basically you set that to calibration mode for scale accuracy. And this is our input attenuator, as you can clearly see is marked here. And then you select your input range here, and on the right hand side here your multiplier. So if you want 3 volts, obviously you put it times 1. If you want 300 millivolts, you put it times 0.01. I think the idea is to get it this range as low as possible before you get the overload light on, and adjust the right hand meter, so you're driving the amplifier not into saturation, but you know, as close to clipping as possible to keep the noise level down, and then adjust this level here to get the correct meter response. On the right hand side here, let me just zoom in a bit so you can see. We've got different meter functions. So we've got root mean squared, we've got impulse. So basically it's like a peak hold meter, like on the old cassette decks, where the meter sort of like hangs slightly on the impulse, but and then comes back pretty quickly. We've got impulse hold, so the highest peak will be held on the meter, and it won't fall back. It will just stay there. So if you've got say for example a peak of say 18 dB, it will jump to 18 dB. Where are we? 18 dB there, and it will just stay there on 18 dB, and it will just stay there on the scale. That's the idea of that. And if you want to reset that, you just press this reset button, and it will reset itself back to 0, and it will peak on the next one. We've got positive going peak, held, negative going peak, and maximum peak. So I think that's basically, I'm not entirely sure between the peak and the impulse, but there was obviously a slightly difference. We've got a linear and logarithmic reading for the display. I'm not entirely sure how that works because it doesn't actually change the range of the display, but it might be logarithmic and linear of the peak hole. I'm not entirely sure about that. Here we've got the frequency time, so that's a response of our meter. And I think that's basically just an adjustment there for probably the RMS. I'm not entirely sure on that either, actually. We need to really power this up and get it running. DC or AC coupled, so if you put a DC input here, I assume it's a direct coupled amplifier. It will put a DC on the output as well, depending on the gain of the amplifier. At the bottom here, there's obviously power, direct input, preamp input, which is this one. We've got a reference level here for checking it, our meter calibration. That should come to the center of the meter. It's on the right range. I've got an internal voltage calibration. I'm not sure what voltage that is, and an external one which you can feed on the back panel. And then we've got various filters. We can connect an external filter in, and you see on the back there's an input and output for the filter, so you can wire it through, for example, a graphic equalizer. You've got normal roll-off filters here, so a low-pass filter, and it looks like a high-pass filter, and various weightings for audio, which is A, B, C and D, which is fairly common in all sound measuring devices. And also these overload lights are actually neons, because it does use high voltage, believe it or not. I don't know why it uses HV, maybe to energize the preamplifier, I'm not sure, but it's transistor amplifier. I don't know why they decided it needs high voltage, maybe to get the resolution on the amplifiers or something. I'm not sure. The possible reason I can only think of is because if they can increase the voltage of the amplifier, you're going to get less current passing through transistors and things, and maybe less noise. That's just my guess. That's a wild guess. Really not sure about that at all. So the purpose of this video this evening is not actually to show you this working, because it works. I've taken it apart and cleaned it up, as I say, is to actually make the thing actually a bit more usable. Now on the right hand side here, you see this socket here where it says battery input. This is a bulging connector, and for those who probably don't know what a bulging connector looks like, it's one of these. And this is the bulging connector, and for those who used to have a blue soldering iron made by Weller that used to have the base station, they use the bulging connectors, as do the some of the quad preamplifiers, the early quad preamplifiers. So it will run off an external 12 volt supply, and it does actually say that it needs up to 2 amps, but when I run it on 12 volts, it's actually drawing over 2 amps, 2.2 amps, something like that. Now I don't know if 2 amps was just a ballpark figure, but it seems to be a bit too much for my 32 Varex Roban power supply, which I have been using on it. It was right at the limit, and the poor old power supply was starting to smell a bit hot. So what I'd really like to do is get this to work on mains, and because it's Brüel Kjær, for some reason they've decided to not use a standard plug. They've used this, I don't know what the hell they call this, but this is not a normal connector, and I can't even get a IEC to be bodged on there, because the diameter of these, the length of these connections here are much less than the connection length here. I was going to just sort of just plug in a mains lead and do away with the earth, but that's not going to be that straightforward. So I think what I want to do, and I have seen there's one of these on eBay, modify this connector so we can actually use a standard IEC connector, and then we don't have to sort of, if I do want to use this thing, which I probably never will, if I do want to use this thing, I don't have to spend an hour looking for its connector. The other option I have seen people do is to basically get rid of this thing altogether, or disconnect it and just run a flying lead inside. But the trouble with flying leads, that means you can't store the equipment away nicely, because if you do that, you've got a lead hanging out the back all the time. This here basically a remote control, I think, as far as I can tell. There's a switch here for remote averaging, and that I think is your voltage input, reference voltage input. I'm not sure. No, maybe not. I'm not entirely sure what that does. This is a trim pot for adjusting calibrations from what I remember in the manual, and this is our voltage calibration. So we put a calibrated voltage in here. It should read correctly on the meter, so we could connect this up to one of our process meters and just confirm the output. And then here are the sockets I was telling you on the back for a an external filter. So basically the output comes here and it's fed back in. So you put say a graphic equalizer between the two. You're basically, it's basically the same as to a preamplifier input and a power amplifier input and a preamplifier output on an audio amplifier. Similar sort of thing, really. So it's just a loop through, really. So yeah, it's in lovely condition, and it just seems a shame that it's not usable. So I wanted to have a look in this evening. Take the car off you. I'll show you inside it, and let's see if we can actually retrofit something in here. I don't really want to start cutting away at the chassis. The other option I have got is to put just a 2-pin figure of 8 sort of like cassette player socket in there. That might be enough room for that, but ideally I would like to get an IEC lead in. An IEC lead would fit in. You can see it fits in there actually perfectly well. I'm not sure the exposure's a bit, don't fit in that way, and it'll fit in that way. So this is a sort of like a Paxlin or I can't think of the name of the stuff at the moment, but let's get the cover off. You can have a look inside and we'll see if we can modify this. Okay, this is the just show you the inside quickly. Obviously not really interested in this because, as I say, it works. We might do a calibration on it, but I have run this through a couple of tests and it seems to be very well calibrated anyway. See how beautifully it's laid out. We've got a sort of like a key here of where everything plugs in. These balls just pull out on these standoffs. You just lift this catch, similar to the HP, and they just slide out. The balls slide out, so easy to work on and easy to maintain. Good quality components. There are probably a couple of electrolytics that need replacing, but at the moment I'm not worried about that. First of all, I want to see if I can do something with this connector on the bottom. So let's have a look at this connector I'm referring to. So we've got this sort of like Paxlin board, or whatever you want to call it, and it's obviously built into the back of the this is the main transformer here. I've got 2 screws here. What I want to do is cut this off and somehow get an IEC lead in the back here. I think it should be fairly straightforward. Unfortunately, there's not enough room to put a filtered board in, because right behind it there's as you see, there's another circuit board, so there's no room to plug anything in. But we should, in theory, maybe if we're lucky, just give you a light in there. It should be enough room to maybe get a just like a normal 3-pin IEC plug in there. So that would be interesting to see if we can get that to fit. So I think the first thing to do is get this removed, undo these 2 screws, lift this off, and have a look at the how much room we have inside to work with. There's not a lot of room to work with, unfortunately, because the wires are fairly short. But this is the incoming. The 2 yellows here, and the orange is the earth. And obviously we've got the selector switch for the transformer to alter the primary to match your incoming power supply or input for your supply. So I think the first thing to do is we need to maybe drill these rivets out. If I can drill these rivets out, we can get this back plate off. That will give us a bit more room, and then we can maybe have a look at sort of maybe drilling this front section out here, and then or maybe even just cut that whole section out. And then mount our IEC lead to the aluminium. So let's drill these rivets out and have a look. What I've done is I've removed the connector, or the actual connections, and this is basically the back plate that comes off here. Drilled the rivets out, got the connector out, so it's left me with this. Now what I want to plan to do is, I don't think this thing needs an earth connection. I could actually make an optional connection on the back foot if you wanted to ground it. They're the 2 inputs to the transformer, and that's the orange wire as the ground. I'm going to just reconnect that back to there when I'm finished. And I've slightly modified this old cassette player D-type plug. The thing is to mount that in there, and then I've got a cassette player type. I don't know what the proper. It's an IEC plug anyway, but 2-pole IEC plug. So that would be mounted in there, probably from the back actually, because of the easier footprint. So I need to take it to work and Dremel out a shape roughly the shape of this, mount this in the back, and then we've got a decent input connection. So hopefully that should work. I'm going to take it into work tomorrow, Dremel that out because I haven't got a Dremel, and see if that's of any success. Look at that magic. Alright, it's 24 hours later. I managed to install a 3-pin IEC plug in there. It was a squeeze and it took a lot of dremeling of the socket underneath, so I'm hoping it's going to fit in okay. It's pretty tight against that circuit board at the back. We can see inside here that this is what I've done. So I machined all the back out and made some sort of like spacers and washers to get it in a bit easier. I don't know if you can see that very well or not. Let's give it a bit more light. But it's in there and it doesn't stick out any further than these voltage selector switch. I might have to put a piece of fiberglass or something behind here. So the next thing to do is let's see if we can get this in. This screw I know it looks like it's cross-threaded. It's not. It's just the way that the screw has broken out to the side of the bit of Paxlin that was there originally. So I just put this was like a penny washer, and then I bent one side of the penny washer at 90 degrees down to give it support. So even though that looks like it's about to fall off, it's not. That is actually perfectly secure. It doesn't look very nice, I know, but you won't be able to see that from the outside. So the thing to do now is to try and get the thing screwed back together, get it in line, check how clearance is between that circuit board, power it up on mains and see how it works. Right, I've got the IEC connector in, but it really is very tight. I think what I needed to really do is build up a spacer to bring the IC connector further to the back of the unit. You see this board here is actually in contact with the with that mains lead, and obviously we don't want mains going straight back into the unit and blowing all the front end up. And you can see that bit of plastic there. There's a thick piece of insulation plastic I managed to get in there that's given me the insulation barrier I need, so that's safe. There's not a problem with that at all. But it really is very tight, and working on this thing, because the transformer leads are so short, you have to be very careful you're not going to break something. But it's all back in together. I think the next thing to do is plug it into the mains, and hopefully the thing still works. But it has been a real pain that the actual connection to the actual back of the unit has been fairly straightforward. Let me just bring the front of the unit down again so you can see. That was fairly straightforward doing that part, but the rest of it was not so straightforward. Getting the connections in the back and keeping them as flush as possible. So ideally I think you need to remount this thing and bring the whole thing out further. Obviously you want this panel back as far as I can as well, to give as much clearance as possible. But it's gone in. Insulation is okay. So we've got that big thick plastic spacer there. That's a high voltage, designed for high voltage. It was out of an old monitor that I had, the XY display scope, the Tektronix one you might have seen. I don't know if you've seen it or not. So there's a bit of insulation there, so that should be working as a good insulator. So yeah, just power it up, make sure it still works, then we'll do some tests on it. Let's power it up, see if it works. The lights come on, I suppose that's a start. So the meter's sort of working, so let's go to direct input. It's obviously not going to pick up noise and things with the cover off it, but it looks like it's working properly. Let's just poke the screwdriver in the input, see if we get any movement on the meter. Yep, that looks like that's working fine. Let's put that to RMS. So it looks like, yep, it's still working fine. It's going to need probably a bit of calibration, but yeah, good. So I suppose the next thing to do is actually run it through a calibration and see how well it works. But at the moment it looks like it's working fine. Not sure why the meter's pegged back like that. That might be a calibration problem. But okay, let's carry on, see what we got. Well, let's give this a go, see what this works like. What I'm doing, I'm feeding from the 8903 audio analyzer. I'm going to feeding a swept signal into the input, and the output is monitoring the output back into the 8903, and we're plotting a chart out with the Peak Millet software. So I'm just going to start a sweep now. Now I expect it to be pretty flat because it's only going to 100 kilohertz. The 8903 will only go to 100 kilohertz, whereas it's a 200 kilohertz piece of gear, so it's well within its spec. But we also want to look, what I'll do is the first sweep. So we've got no filtering in, no weighting is implied. We should get a perfectly flat response. So let me start the sweep. Starting now. I don't know why the meter dropped back like that. That would imply that there is actually something wrong with this instrument. Just looking at the responses now. Yeah, it's got quite a significant roll off for some reason. I'm not sure why. I think it's something to do. I think there is actually a problem with this unit. In theory, it should be flat from 2 Hz to 200 kilohertz, and certainly the output I'm looking at the moment doesn't look like it is. So let it run through. We are now at 63 kilohertz. Okay, we've completed the trace. Let me just show you on the Peak Millet software what's going on. Zoom in. Now it looks to me. Can we get it back on the scale? That is far from being flat. So we started at plus 55 dB, it's dropped down to 0 and then gone back up again. So I'm not sure what's going on there. That to me, I don't think is right. So I need to check again, see if I can work out what it is, and try it again and see if we can get a better response. Right, let's run this again. AC coupled this time, that might make a difference. I've got full scale deflection. We're putting 1 volt into the unit. Let's just zoom in a bit closer to the needle so you can see what the best resolution you can get. I'm going to start the sweep now, starting from 20 Hz and ending at 1 kilohertz. Okay, and I'll just read out the frequency for you. So we're just passing 20 Hz now. It's quite a slow sweep. I want to get the best resolution I can. I'll leave this to run. We're just looking for any deflection at all on the meter here. This will give you an idea of the roll-off and things like that. I'm looking at the audio analyzer's dB reference point. So it started at 0 dB, at 20 Hz, and it was at 0 dB. We're now at 400 Hz, and it's flat, totally flat, which is looking good. So let's let it run, and you can see the meter isn't moving at all. So the input of the amplifier looks pretty flat so far. We're now coming up to 2 kilohertz. Yeah, just passing 2 kilohertz, and according to the analyzer, we've dropped 0.02 dB. Now that could be the analyzer itself. It could be to do with the couplings of the leads. It could be the B&K, but really 0.04 dB. Now who cares? That's flat in my mind. We're at 20 kilohertz, 25 kilohertz. And I'll show you the plot when I've finished. I'm just ending the plot now at 50 kilohertz, coming to the end of the sweep. And it's ended the sweep. And you see that the meter's gone back to the beginning of the scale, so there's no output from the generator anymore. Let's have a look at the chart response. So what I'm going to do is going to maximise that. Won't make a lot of difference, I know. Actually, what I'm trying to do is just try and avoid the camera getting overexposed or underexposed, which it can do with this camera. So let's have a look. I'm trying to find you somewhere where you're not getting any glare, which is a bit difficult. Okay, let's flatten the screen out. Remember how to do it, of course. There's a plot limit you can adjust here. Can't remember how to do this. I might have to replot this out and put it in at a later stage. But you can see that's a 0 dB line, that's -5 dB, and you see it's flat all the way through to 100 kilohertz. So, where are we? I don't know what I've done. Bear with me a minute, I'll try and get this back again. I don't use this plot this very often. Okay, let's get this plot back and I'll try and sort it out so you can actually read it. Okay, a lot of messing around, got the response out, and you can see it's absolutely flat. There's 1 dB per graticule, and we've got a very, very slight rise on the top end. So, yeah, that was good. Very good response from the amplifier. So the next thing we'll do is we'll do a sweep with the one of the filters installed and see what that does. Right, the basic flat response of the analyzer or the meter has been sort of like confirmed that it's pretty good. So now we're going to just check the filters, see if they're working properly. So we're on D-weighting and see what response we get here. Now I expect a low frequency roll off, a peak in the mid-range and a roll off again. I'm showing you on the meter. I'll read out the frequencies that are shown on the analyzer. Also, I can't get everything in frame at the same time, but I am also plotting it out on the analyzer's software, which is the Peak Millet software. So we'll get a chart at the end of it, and I'm going to do 3 plots, and then I'll have to start a new fresh plot. But let's start the plot now. So reference is set OK. So we're starting at 20 Hertz, and you see there's a massive roll off here. It's a fairly fine sweep here. We're doing it basically, the analyzer does in steps frequencies. It steps to the next frequency, measures it, steps to the next frequency. We're now at 100 Hertz. You see the gains rapidly coming up. It'd probably be better if I did it on a dB meter, but you can see it's come up to, it's basically back to flat at 400 Hertz now. And looking at the chart here, we've got a nice low frequency roll off. You see the levels are staying pretty flat, and eventually I expect to see the level falling away again. We're now at 6 kilohertz, 10 kilohertz. Here we go. Rapid fall off, 15 kilohertz, 20 kilohertz, 25, 31, 40, 50, 65, and the end is. So yeah, there we go. That's clearly that filter's obviously doing something. I'm not sure if that's right for the weighting, but I'm sure it's probably pre-programmed in. It's probably unadjustable. So that appears to be working correctly. So we'll move on to the next weighting, which is weighting A. Just selected weighting A on there. I'm going to start that, and the weighting A will be with the next trace. So we're starting now. Oh, just starting the sweep. 50 Hertz. At the moment I can't see what trace it is because it's off the scale. The software is auto plotted, so I can't see what colour trace it is. Okay, it's a blue trace, and it's got a steeper roll off. It rolls off earlier, and you can see that the meter's coming up now. That's at 400 Hertz. Okay. Two kilohertz now, and so we're more or less flats now. And this is more like a notch filter, not so much a notch filter, a bandpass filter. I think it's a better word. A notch filter is usually sort of like got square sides, but this is the blue chart you'll see in a minute when I show you. But it's like a. Yeah, it's just like a mountain. It sort of comes up at 100 Hertz and drops down at looks like about 30 kilohertz or something like that. So that appears to be working correctly as well. Let's move on to the next weighting, which is weighting B, and this will be path C, track 3. I'm sort of talking to myself aloud. Okay, so it's starting now. It should be quite interesting because it will plot out all these graphs and superimpose them on the display, so you'll be able to see how the different weightings work. And actually this plot looks very similar to the waiting D. Actually, it's coming up quite quickly, and it looks like it's about to level out now. We're at minus 0.25 dB at 500 Hertz, and we're leveled out now. We're flat at 1200 Hertz. Yep. We've got a fall off again now, starting to rapidly fall off. 4 kilohertz, we're minus 2 dB. 8 dB, we're minus 3. Minus 15, we're at minus 8. At 20 kilohertz, we're at minus 10 or so. Yeah, rapidly falling off. Okay, we're at minus 1. Okay, and that's the end of the plot, and it's finished. And that's very similar to the first plot, but maybe... yeah, I'll show you the charts afterwards. It's hard to describe them, really. And then we'll just print them out, maybe. So let's go to waiting C. And that'll be the final plot that I can do on the peak minute software before I have to restart the program again. So let's start on waiting C. Interesting enough, that started at much higher, less roll off. We're at 400 Hertz. Pretty flat at 1.5 kilohertz. Starting to fall away now, 4 kilohertz. 1 dB at 5 kilohertz. 2.5 dB at 8 kilohertz. Minus 5 at 10. Minus 11 at 20. Okay, basically the plot's about to finish now. Okay, so it's finished. So let's have a look at the, turn around and have a look at the plot. And that's the final result. It came out quite clearly. Basically, I printed out the response I got from the peak minute software and just labelled them up, so it's a bit easier. Managed to spell response wrong, as I usually make some spelling mistake on something I type. I don't know why I do it. So backwards brain or something. So there's the responses. The blue is the A waiting. B is the purple. D is the yellow, and C is the green. And it's the green is actually not that easy to see, but you can see it here. Let me just point it out. It's the green tracks along here and comes back down here, so it's fairly flat in response to the others. Funny enough, I looked up the weightings on the on Google, and this is exactly right. This looks perfect. You know, the response of the units working perfectly well. So a really nice, another nice piece of gear. I know I say all my gear's nice. Another nice piece of gear that's far too good to be thrown away. This thing was apparently been sitting in someone's workshop for sort of 10 years. You know, he'd bought it as a job lot and never used it, and it works perfectly well. And you know, apart from, you know, the power lead needing to be sort of standardised to an IEC lead, contact cleaner on the switches, and that's basically it really. All the capacitors seem to be fine. It's been on for sort of like a number of hours. I had it on at work for sort of like 7 or 8 hours and no problem at all. So yeah, I'm very pleased with this. Interesting piece of gear. Nice to use the 8903 and the peak minute software to plot it out, and it's done an excellent job. Hope it was of interest. Thanks for watching, and stay safe everyone.